It's right about 2:35, so I'm going to go ahead and let everyone know that we will be recording this session, um, and we thank you everyone for attending. And I'm going to go ahead and hand it over to you, John, for a quick introduction and let everyone know what we're here to see.
Sure, thanks. Thanks, folks, for joining us. This is going to be a great conversation and presentation by Torre Jorgenson on the permafrost in Alaska. And I am John Morden. I'm one of the directors for ALICE, which is Alaska Institute for Climate and Energy. And we are hosting this along with Alaskans Know Climate Change, the Kachemak Bay Conservation Society, the Sunrise Movement in Alaska, and Alaska Takes a Stand. This is kind of sort of an inaugural webinar for us, and we realized the other day that we kind of missed a huge opportunity with the pandemic, and we should have been doing this all last year, but that's fine. We're starting now, and just to give you kind of a heads up, we're going to have one on May 11th, and we'll have marine biologist Rick Steiner joining us, who will be giving us a summary of the current science on the impacts of climate change in Alaska's ocean ecosystems, ocean habitat, seabirds, marine mammals, coastal communities, and importantly, what we can do about it. And that'll be on May 11th. And then on June 8th, we'll have Zav Grabinski, who's from the Alaska Fire Science Consortium, and he'll be talking about Alaska's changing wildfire environment. And then we'll be taking a summer hiatus and starting this back up in the fall. I think at this point, I'm going to turn this back to you, Mike.
Sure. Just a couple quick housekeeping items. If you do have any questions, again, we'll have folks put your questions in the chat, and we'll be keeping an eye on that for the Q&A at the end. We do have everyone muted right now, so everyone will be able to hear the speaker. And without any further ado, I'll go ahead and turn it back to you, John, for the introduction of Tor.
Sure. So this is a real pleasure for me to introduce Tor. I've known him off and on. We were trying to decide when we actually met, but I've known him off and on for quite a while. Any rate, Tor is the owner of Alaska Ecoscience, and it's a small business in Fairbanks, Alaska, dedicated to research on Alaska's changing landscapes. And he's also an affiliate professor with the University of Alaska Fairbanks. He has worked on ecology and geomorphology studies throughout Alaska for nearly 4 decades, focusing on ecological land classification and terrain mapping, coastal studies, ecological restoration, permafrost dynamics, soil carbon, and climate change impacts. Internationally, he has been involved with the International Permafrost Association, Arctic Coastal Dynamics Program, and the Circumboreal Vegetation Mapping Program. In 2017, he received an honorary doctorate from the University of Alaska Fairbanks in recognition of his contributions to ecosystem and permafrost science in Alaska. So, Tor, take it away.
Okay, thanks a lot, John, and thank the Alaska Climate Action Network for the opportunity to present my talk on permafrost history and vulnerability to climate change in Alaska. So what can we learn from the past to project what might happen in the future? And did we get a change in slides here? So the topics I'd like to discuss today are kind of the various aspects of permafrost formation, and then later the degradation of permafrost, and then finally the implications for ecosystems and society. In the simplest sense, permafrost is composed of three main characteristics. It has a thermal regime that has a temperature gradient from the surface down towards the zero temperature at the base of the permafrost. And then it has a fluctuation of temperatures up at the surface. And at some degree, there's no fluctuation of temperatures at the zero annual amplitude. And then the soil thermal climate and soil thermal regimes interact with geothermal processes to affect the soil texture, and then in turn soil texture from silt, varying from silt to gravel, affects the types of ground ice that can form, and the thermal regime with its gradient through the soils also affects the movement of water through the soils as in response to different matrix potentials. But it can get a lot more complicated than that. There are many factors interacting to control permafrost formation and degradation. And in the simplest terms, we have a series of state factors across the landscape that include geology, climate, the vegetation, microtopography, and microclimate. These affect the surface and subsurface conditions of groundwater, surface water, organic matter, and then these translate into soil water thermal regimes that affect water temperatures, surface temperatures, and these control the fluxes of heat, both vertically and laterally through the soils, affects adjustment of the active layer, and then ultimately determines whether permafrost grades or degrades. And then these are affected by a series of feedback, mostly related to positive feedbacks from water at the surface or the negative feedbacks from vegetation and soil organic matter accumulate, and those loop back through the surface properties. A great thing about Alaska for permafrost is it makes a great permafrost laboratory. We have a temperature gradient of almost 13 degrees C, all the way from Barrow at about a -11 down to the last bits of remnant permafrost down around King Salmon at a mean annual air temperature of +2 degrees. Then we also have a wide diversity of superficial materials. Here's a map that I've modified from Karlstrom of surface materials across the state. And I mostly want to focus on a few of them in this talk. And that's these tan brown areas of hillside, residual soils, and weathered bedrock. That's one of the dominant materials across the state. And then we have a very special material, legacy of the Pleistocene in terms of these Aeolian lust deposits in yellow. And there's a large silt belt across the northern part of the state and quite a bit on the Seward Peninsula, and then around the Yukon Flats and a little bit around Fairbanks. And then one of the fascinating deposits for studying permafrost degradation and kind of the feedbacks between vegetation, soils, and permafrost are on these abandoned floodplains and terraces in dark green. And then I'll mention kind of a special type of ice, of buried glacial ice in these blue deposits that both in the Brooks Range, Alaska Range, and even extend down into the Gulf of Alaska. In addition to these climate and surface materials, there are strong ecological feedbacks from kind of the vegetation and soils, ecological processes. So here we can have permafrost degrading at a mean annual temperature of -11 degrees C due to surface impounding on this water. And here's what the subsurface could look like in terms of these massive ice wedges that can be highly sensitive to changes in surface conditions and climate. And here we have permafrost persisting at a mean annual temperature of +1 degree C down at near King Salmon. And here's a nice view of this ice. So here we have 13-degree range in temperatures. And we also can have permafrost degrade up in the high Arctic, say Violet Island, at temperatures of -16 degrees. So these patterns are largely controlled by the influence of surface conditions. Here's an illustration or some modeling results trying to quantify the effects of vegetation and soils. Some modeling that Vlad Romanovsky did for a paper in Canadian Journal of Forest Research, where we modeled the ground temperatures in relation to barren silt all the way to a late successional ecosystem to a tussock bog. And we found a range of subsurface temperatures varying by 5 degrees just in association with changes in vegetation. And then when you add water to the surface, that could increase the temperature from almost -4 to -8 degrees. So just about a 12-degree range in temperature, just the difference in ecological conditions at the surface. And this range, due to ecosystem responses, is almost double what could be the vulnerability to permafrost due to climate change. And so these ecological processes in the central portion of Alaska result in a discontinuous permafrost distribution, with permafrost often related to tussock bogs, black spruce forests, and permafrost on the north side of bedrock hills. So when we look at the effects of both climate and ecosystems, we can kind of partition the types of permafrost depending on these two drivers. And we can conceptualize it as very cold areas where climate is a sole driver of permafrost. And then much of the North Slope is climate driven and ecosystem modified. So in early successional stages, climate initiates a permafrost, but then changes at the surface modify the permafrost characteristics and ground ice. And then when we get into the boreal region, kind of the subarctic climate, we find that the permafrost distribution is mainly found around King Salmon on the Alaska Peninsula, as protected by ecosystems and can no longer be formed under the current climate. So typically our concept of permafrost was in terms of its continuity, whether it was covering 90% of the landscape or 50 to 90% in terms of discontinuous permafrost, or these sporadic or isolated areas with rare occurrences of permafrost. And then we can see that the permafrost depths range from 660 meters up at Prudhoe Bay. In central Alaska, it's often 60, 70, 100 meters thick. And then when you get down to Glen Allen, we're in the 30 to 40 meter range. And around Anchorage, there are a few isolated permafrost patches, 9, 10 meters thick. So in the recent work here that we've got in review, we tried to make a new permafrost map in relation to climate and ecosystem processes. And here we have Alaska upside down, where we have a little bit of climate-driven permafrost in the Brooks Range, where ecological processes have very little effect, to these climate-driven ecosystem modified on the North Slope, to ecosystem driven in the boreal, and then ecosystem protected down on the southern portion of the boreal. But permafrost changes over time, and here's kind of a persistence of permafrost through the Pleistocene going back 800,000 years. And Prose has documented persistence of permafrost in the Yukon territory at least 740,000 years old. So it's gone through many interglacial periods and has been able to survive from this ecosystem protection. And then down around Glen Allen at Palisades, we have some permafrost that's older than underlies this 124,000-year-old Old Crow tephra. during this cold period. And then we have a terrific permafrost observatory in Fairbanks, the Fox Permafrost Tunnel. And that's mostly preserving permafrost that's formed during the late Pleistocene period from 50,000 years to 10,000 years. So this late Pleistocene permafrost has left a legacy of different types of ground ice and permafrost conditions. The types of landscapes I'd like to talk about here now are types of geomorphic landscapes formed particularly during cold periods, and that's this loess deposition during glacial periods and also glacial deposits. And then I'd like to talk some about abandoned floodplains, mostly formed or persisting through the Holocene. And right now, my life is deeply impoverished by the lack of Pleistocene megafauna. And now I worry about my life becoming more impoverished by the loss of some of these late Pleistocene permafrost deposits. So we have some outcrops of glacial landscapes, glacial ice in various regions of Alaska. Here's a thaw slump up at Toolik Lake that's showing some persistence of remnants of glacial ice, buried glacial ice from about 65,000 years ago. And this is what it looks like with this entrained deposit suspended within the clear ice. And you could turn this as being climate driven by the late Pleistocene cold climates, and now it's protected by ecosystem processes at the surface. But we also have buried ice, glacial ice from the Little Ice Age, and here's some buried glacial ice in the Malaspina Glacier down around Yakutat. And then here's buried glacial ice in the Muldrow Glacier and Denali Park. So large, massive deposits of buried ice. And once glacial ice becomes stagnant and buried, we claim it as permafrost. So we make a nice grab into a transition from glacial to permafrost conditions. Also during these glacial periods, especially during deglaciation processes with a lot of glacial outwash, large grade plains, there was a lot of windblown silt prevalent under these glacial conditions. And this has resulted in large deposits of extremely ice-rich Pleistocene silt. The Russians have a nice term for it, yedema, specifically for these uniquely Pleistocene deposits. And here's an exposure that we've studied for nearly a decade up along the Killick River in northern Alaska. And these are very large syngenetic ice wedges that keep on forming as the silt accretes at the surface and chugs on up, and these ice wedges just extend on up. And we can see two periods of ice wedge formation, one with very slow accumulation rates and large ice wedge development, and then high accumulation rates and small ice wedge development. This is about 30 meters high, and the total ice content of this exposure is about 80% ice. We also have those deposits are extensive through the interior. Here's an exposure along Birch Creek, and it also has these very large syngenetic ice wedges, and they probably comprise 80% of the volume of this exposure. So extremely ice-rich materials in these Pleistocene deposits. And we can also consider this to be climate-driven and ecosystem-protected permafrost. It formed under a different climate, but now is protected by this thick layer of silt at the surface and this draping of organic materials and a forest cover. So in terms of its distribution across the state, this map highlights these Yedema areas with extremely high volumes of ice. I showed you one picture of it, Ecological, up in this silt belt along the north slope. And then the second picture I showed was of Yedema along this silt belt above the Yukon Flats. We have isolated portions of it around the Fairbanks area, and then large areas of it in the Seward Peninsula, Kobuk, and Inoko and Koyukuk regions. Here's a DEM of the Yedema and Yukon Flats, the silt belt north of the White Mountains. And this area is so ice rich that it deforms almost like a glacier in terms of developing crevasses as these deep thermokarst lakes develop and the silt Yedema starts moving towards those low areas. And this is perhaps the most ice-rich landscape in the state. When I did a bathymetry for this boot lake, the lake itself was 22 meters deep. And then if you get up to the old shorelines, that's another 10 meters. So its total collapse is about 31 meters in this deposit. And then lastly, in terms of permafrost formation, I'd like to talk about permafrost developing during floodplain evolution. And here's an example from the Colville Delta where you have migrating floodplain with bare silts and sands at the point bar. And then we have the first stages of ice wedge development at about 500 to 1,000 years. And then after about 3,000 to 4,000 years of evolution, we have extremely ice-rich deposits on the upper abandoned floodplain. And during this transition, we've been able to map and document the changes from pore and lenticular ice in these early successional point bar deposits to extremely ice-rich silts in the distal portions of the floodplain. And this is all under a fairly uniform climate regime. So these are due to changes in vegetation and soils at the surface. So it's a ecologically modified permafrost. And we can see that the ice wedges grow and modify and become denser over time. And here we have very large ice wedges at intermediate levels of succession, and then a very dense network of small but deep ice wedges at the latest stages of ecological development. And here's what an ice wedge can look like from an exposure along the riverbank. And typically, ice volume can be 10 to 20% of the upper 3 meters. Occasionally, it can get as high as 40% of the upper 3 meters is composed of these ice wedges. They have a very thin layer of active layer and some little bit of permafrost at the top, this transient layer that protects these ice wedges. And this ice wedge is probably 3,000 to 4,000 years old, and it has been able to persist through various climate fluctuations due to this level of protection at the surface. But we also have permafrost that can form during small climate fluctuations in the recent period. And here are some birch forests that developed on permafrost plateaus that developed in the 1960s. They weren't evident in 1949 photo and first became evident in the 1980 CIR photos. And then here are some newly developed little permafrost mounds that I found in on the Kantishna Flats. And then recently I found these little permafrost mounds that formed on the Mud River Flats. And I kind of attribute those to some periods of cold temperatures with low snow in the 60s, also in the 90s, some very cold temperatures with low snow conditions. And then in about 2007, cold temperatures again with low snow conditions. So quite sensitive to variations in climate. Through studying of these different types of terrain and different deposits, we've accumulated a large database of ground ice volumes in relation to depth. And for some different materials, glacial marine materials, the segregated ice contents are 80 to 90% of the upper 3 meters. And similar on the coastal plain, much higher variability, but often in the 70 to 80% range. Sand is relatively ice poor. And then these silt, Aeolian silt Yedema deposits are also extremely ice rich. And then I talked about the floodplain evolution accumulating more ice over time, getting up to 80 to 90% ice. So we've been accumulating knowledge of permafrost characteristics through the last 50 years, and our knowledge has increased from Farian's map in 1965 to Brown's permafrost map in 97 to a permafrost map I developed in 2008, and then a newer version for Northern Alaska in 2014. So we're increasing our resolution in relation to surface deposits and how much we know or can quantify about ice with depth. And then more recently, Neoplastic has been able to use remote sensing and our large set of data from ground observations to match them up to map modeling permafrost distribution. So pretty much continuous permafrost distribution in Northern Alaska, some very isolated patches down in the Alaskan Peninsula, and then discontinuous mix here in the interior. So now I want to focus the next portion of the talk on permafrost degradation, and here's just a slide illustrating the wide diversity of responses to of how permafrost can degrade to development of fens, to pits and forests, to ice wedge pits, from ice wedge degradation to thermokarst lakes and bogs, to badger X developing, to coastal bank collapse in long coastal erosion, to thaw slumps, to active layer detachment slides. So depending on the ice and the climate and the disturbance, you can get a wide range of terrain responses. And they can occur over different time periods. We can have ice wedges melt out in terms of years, or after a fire, thaw active layer detachment slides kicked off in a matter of days in the Anaktuvuk fire, or we could have kind of glacial thermokarst and thaw slumps also developing over years to decades. And then some of these deep thermokarst lakes with Yedema can take millennium to develop. One way to simplify this complexity is to divide the landscapes up into upland landscapes and lowland landscapes, and then whether the material soils are loamy and peaty or rocky and sandy. And so here in the rocky uplands, we mostly have thaw stable materials that comprise about 45% of the region in the interior. Then we have these sandy lowlands that comprise about 6% of the interior that has these very distinctive thaw sinks with permafrost degrading and the water draining down these sinks. And then in Yedema silty uplands, we have these deep thermokarst lakes developing, and 20% of the interior has shallow thermokarst lakes, bogs, and fens denoted by this lateral surface runoff and degradation of bogs to lakes to fens. So in upland, rocky uplands, here's an illustration of ground ice in the top 1.5 meters. And some of these rocky areas can be quite ice rich, but when they thaw, there's enough plastic material in there that they're fairly stable in terms of surface movement of materials. And you can see that there's been repeated episodes of permafrost aggregation and degradation related to the subduction of organic materials through diaparism. So the water moves up during thawing through the soils, and other materials move downward to replace as pore spaces or lack of those thawed volume spaces in the soils. And then the silty uplands, we mostly have these microlenticular to microataxitic structures, but also those large syngenetic ice wedges that I show you related to Yedema. And when you have those differential volumes, you get differential thaw settlement. And here's an example around Fairbanks of these thermokarst troughs over large Pleistocene wedges, and then the related mounds in the high centers. And over the last decade or two, I've seen a lot more of this developing in the Fairbanks area than I remember in the past. Another thing unique about Yedema related to those large syngenetic ice wedges is the development of sinkholes that go down through this ice wedge network. And here's a hole collapsing at the surface. And this helps protect Yedema through the ages, because they are a way of shunting water off of the surface. And water is kind of the death of permafrost. And if you have a way to remove that impounding water, you can maintain a better heat balance. And I found a dog once that had fallen into one of these holes. And so they're pretty prevalent around Fairbanks, one right down by my mailbox below my house. Then for sandy lowlands, I mentioned 6% of the landscape. They're prevalent in the Yukon Flats, Kobuk Valley, Kantishna Flats. And these sand sheets have high water infiltration rates, so water cannot really be impounded without permafrost. And there's been widespread degradation in the last 50 years. And here's what the drainage pattern looks like on the Yukon Flats. Bert Minsley's done some helicopter electromagnetic imaging, and these talus form below the lake, and so they're surrounded by a kind of a permafrost curtain that impounds the water in these lakes. And if you develop a tunnel through this permafrost, then these lakes can drain quite rapidly. And you end up with a surface like this. I call it a thaw sink caused by the draining of permafrost contained lakes. They're not permafrost lakes because they don't have enough ice in the sand to form from thaw settlement. And these are undergoing a shift from waterbird habitat to perhaps bison habitat to forests. And then silty peaty lowlands, they're in probably the fastest state of transition, where here in the Kobuk region, there's about 40% of the lowlands have degraded to an Inoko flats at a mean temperature of -2, almost 80% of the landscape's degraded. And then a concept of how it might look in the future are these Oppelmeyers and the Susitna flats, where less than 1% of the landscape now has permafrost, and there's abundant peat wetlands across the region.
Just a 10-minute warning for you there, Tor.
Okay, thank you. So here's a view of collapse scar fens on the Tannoff Flats with these drowning forests. And here's a moat that forms along the margin of the edge of these collapsing forests. And here's an aerial view with the long linear feature of groundwater driven fens. In the Innoko Flats, the development of these shallow thermokarst lakes are often being infilled by these shore fens, and then you have these remnant patches of peat plateaus that are so oligotrophic that they become dominated by lichens on the surface. In the Innoko Flats, the degradation has been ongoing for almost 1,000 years with a rapid increase. So these bright green areas are only 10 to 20 years old, and these interior old bogs can be as old as 500 to 1,000 years from earlier degradation. In contrast, on the Tannoff Flats, most of the degradations happened during the last 100 years. And here we are in our instrumental record with our oldest bogs 500 to 1,000 years and our youngest fens only being a few decades old. Many of these flat areas have gone through repeated histories of degradation and aggradation. These bright yellow peats, sphagnum riparum, indicate periods of past thermokarst. And so you have a early succession in the bog to forest development to thermokarst peat again, and back to forest development. Many of the silty lowlands in the interior have an abundance of thermokarst lakes, and many of the refuges in the fish and wildlife system have been developed in around these areas of extensive thermokarst lake development. So these lakes, and as well as tussocks, are a few of the only totally permafrost dependent systems. So these thermokarst lakes depend on being surrounded by permafrost to form these impounded water bodies. If you lose, and when you lose the permafrost that surrounds these lakes, then there's no mechanism to maintain and contain that water. So in my opinion, these are the most endangered ecosystems in Alaska. And then Tussocks Areophrum vaginatum, it's the only species I know that's totally dependent on permafrost. And a couple words on thaw slumps. Dave Swanson's mapped 276 of these bright green thaw slumps related to buried glacial ice. And here's what it looks like. And the material slides on this thawing front on top of the buried glacial ice and makes supersaturated soils, and they can slide off that ice very easily. And then another type of ice wedge, massive ice, are these ice wedges, and the current degradation of ice wedges is rapidly transforming the landscape in the Arctic refuge. So these are all these thermokarst pits developing over thawing ice wedges, and these have formed over the last 2 to 3 decades. And it just shows there's some ecological transformation responses to this ice wedge formation, where it can go from open water to aquatic sedges to being fully overgrown, and completes a cycle of processes. Here's just some information on the rates of degradation using air photos from 1949 to the photos in 2009 and 2012, showing that aerial extent has increased from about 1% over to 8% over this period from 45 to 2012. And then because permafrost can be ice rich along the coast, it can have a large effect on coastal erosion, with some areas of having up to 16 meters of erosion per year along Cape Halkett. A lot of this is due to this ice wedge, and you have these block falls and thermal niches erosion, and then the blocks falling down. We also have permafrost degrading on the YK Delta, both due to storm surge salinization and then accumulation of water in these little pits. And as I mentioned, water is kind of the death of permafrost. And once you start fragmenting the surface with these thermokarst pits, you can accelerate the rate of degradation. When we look at the general abundance of these various types, we find that thermokarst pits and troughs related to ice wedges are most abundant in the Arctic, and thaw lakes also in the Arctic, but bogs and fens are most prevalent in the subarctic. And when you look at the total extent, about 10% of the Arctic's been affected by thermokarst features, and 5% in the boreal region. So it's strange, there's actually more degradation going on in the colder Arctic than there is in the subarctic, and it's related to prominently to these ice wedges. And then for a little bit of look into the future from Vlad Romanovsky's modeling over the next 50 years, we see that the thermal regimes are permafrost is very high risk from warming over the next 50 years, both in the YK Delta, Southwest, and then interior Alaska. And these have been documented through temperature monitoring network, where we see increasing temperatures in northern Alaska and some in the interior. Some areas have reached near zero, so there's no change just because they're at the melting point already. And a couple of words on fire as accelerating degradation. Here's a fire in 2001 that caused a collapse of the surface from a forested surface to now it's down below water. So it's the first time I've seen a forest actually collapse below water due to fire. And an immediate disturbance like that can also cause thaw slumps or active layer detachment slides in Yedema regions. And a few slides on the consequences. Here's some impacts from winter seismic exploration, where these trails now are become permanent features in the landscape due to wintertime disturbance related to this prevalence of ice wedges and extremely ice-rich soils right below the active layer. And it's causing a substantial amount of damage to our infrastructure in the interior. Here's damage to the Coke Cutoff Road. Right below my house in Belaine, we have these development of thermokarst moats along the sides of the road that are underneath the road bed. And this is probably the most expensive stretch for road maintenance in the state, right here in Goldstream. And one of the approaches to try to mitigate that is through insulating the road bed. And it's a kind of a short-term solution for maybe a decade or two, but we still have this development of water moats along the sides of the roads. And it's causing extensive damage to our power lines and roads. And now I'm getting more frequent calls from landowners about what to do with their settling and damage to their house. And quite a few hundreds of houses in Fairbanks are built on this extremely ice-rich Yedema. And then in coastal regions, Utah is a sad example of the development in permafrost and related to storm flooding. And now there's a lot of effort going into relocating Utah, and 27 million was spent the previous decade, and they may need 100 or 200 million more to be able to complete that move. So large federal, state, and village liabilities and needs to make that happen. And then in terms of some other land use, in the YK Delta, there's use of these permafrost plateaus for fish camps. Field research camps use these permafrost plateaus. They're good habitat for cloudberries. A lot of archaeological sites on these permafrost plateaus, and fish and wildlife research facilities use these higher land areas. So in the YK Delta, I consider it to be the most vulnerable region in Alaska, and this lighter pink area or purple areas that are very low-lying flat areas with permafrost that are going to undergo flooding, salinization, and thermokarst over a large region. And Newtok is right on the edge of these materials. And then finally, kind of the last slide, there's a potential for a large permafrost carbon feedback, where as these organic rich soils thaw and the active layer increases, it thaws this carbon that's been accumulated over many millenniums, and that carbon can be released through microbial processes, both aerobic for CO2 and anaerobic for methane. And this thawing the pools are extremely large in a global context at 1,300 to 1,600 pegagrams of carbon, and an estimated loss right now of 300 to 600 million tons of net carbon per year. So in conclusion, permafrost can degrade in cold climates and persist in warm climates. And this complexity of aggregation and degradation is a response to interacting state factors. And much of the evolution of the permafrost landscape is dependent on ground ice that's formed over decades to hundreds of thousands of years, and resulting in a lot of different types of permafrost degradation ecological responses. So in sum, the vulnerability of permafrost lacks a simple answer. It depends, because there's interaction, these thermal responses, thaw settlement, and ecological feedbacks. And then most permafrost in central Alaska will be lost over the next century with large ecological and societal consequences. So I've used up more than my time, and thanks for listening. And if you have a few questions, I'd love to see if I could answer them.
Yeah, we did have just a few questions here so far, Tor. And again, anyone that hasn't asked a question that's burning, please feel free to put it in the chat. But one of them is from Ilya, and they were very interested in seeing methods of controlling the water runoff, given the profound impact that you showed it has on the accelerated soil degradation, particularly with it affecting folks in Fairbanks and the increasing rain and northern facing hillsides.
Well, there's several aspects of water runoff. One is the changes in runoff from glaciers retreating that has changed the volume and frequency of flooding on floodplains. That's not so much of a permafrost question as it is a glacial question. But the thawing is affecting our overall seasonal patterns of runoff and storage, so that there's been a trend towards increasing winter runoff in the Yukon River basin that's related to more movement vertically down through these upland soils down into the groundwater system, and then base flow exiting the system into the river systems during the winter. So a shift from overland flow during summers to winter flow through the groundwater system.
Thank you. Another question that just came in here is, do we have an estimate of the methane emissions? And I think you had a carbon estimate on the last slide there, but it goes on. In addition, is there an estimate of how much will be released when the permafrost inevitably melts?
Well, I don't have specific numbers for you, but I think that's emerging to be the greater concern. And that's because, especially these lowland areas, when they impound water, it creates an anaerobic system. And these can be extremely high hotspots for methane emissions, particularly in Oko Flats and Koyukuk. NASA monitoring through using airplanes and methane sensors have found really high methane emissions over these bog and fen areas. I didn't have the opportunity to mention subsea permafrost and these frozen methane clathrates, and that is perhaps the largest wild card. There's our largest methane deposits are these cold, solid methane clathrate deposits maintained by cold temperatures and pressure. And there's been some studies of large ebullition loss of these clathrates over in the Siberian shelf. And it's poorly studied, undocumented, but perhaps the largest wild card in potential release of methane to the atmosphere.
Yeah, it's very, very concerning. Another question was with the results of climate change in Alaska, is that affecting the lower 48 and how that's progressing with the question wasn't fully yeah. Do you see effects in the lower 48 as a result of Alaska's climate change? How's that understanding progressing?
Well, the biggest concern is through this permafrost carbon feedback, and the concern is for these large sequestered carbon deposits, masses in permafrost, and the thawing of that, and then degradation. So it's more a global concern that can affect climate patterns and the jet stream. And so the permafrost carbon in Alaska is of direct concern both globally and to climate patterns in the lower 48.
Hmm.
But
Um,
there is some controversy over it because as soon as permafrost degrades, the whole system reorganizes and it allows for growth of new vegetation, new peat, and particularly like upland soils with the thinner carbon deposits that are very prevalent in Alaska. The new growth of deciduous forests may accumulate more carbon biomass than is lost from permafrost degradation. So quite a complex landscape.
yeah, yeah. We had a more basic learning type question of Kelly looking for an example of an ecological feedback that would reduce permafrost degradation in warmer temps. So, what are some of those things protecting the permafrost ecologically?
Yeah. Um, so what protects permafrost across the climate gradient are late successional ecosystems, and it has some important management implications. And there's been discussion among the fire management operators and land managers, such as the Yukon Flats, whether they can manipulate the fire regimes to promote late successional ecosystems and help protect the permafrost through these ecological protections. So that's kind of the main way, um, being able to use the successional patterns. It can take decades to get back to a thermal regime that's stable for permafrost. So it's quite a slow effort to reestablish permafrost after it's lost. But you know, for every change, there's winners and losers, right? And there's very few species that are totally dependent on permafrost, but like I mentioned in the talk, the lakes are probably the utmost concern.
Well, thank you so much. Another question here that's come in is the definition of solidly frozen. I think just to clarify.
Yes, so when you get near zero, a lot of things happen to soil and water related to the matrix potential of the particles. So a lot of our permafrost around Fairbanks is getting near zero, and there's a substantial unfrozen water content at minus 0.2 to even minus 5 degrees. There can be some unfrozen water, and water can move through those soils along a temperature gradient. And when I'm coring permafrost now in the interior, I'm often encountering fairly soft, malleable permafrost related to this high unfrozen water content. The other way it expresses is on the thermal regimes, it's locked into near zero at a phase change. So part of the soil is frozen and part is unfrozen, and it can't go above zero because there's still some frozen materials, and it can't go much below zero because it takes freezing of water. So it's stuck at this phase change transition.
All right. Well, that that gives a good difference there.
So if there are no more questions, I'd like to thank everybody for taking the time to attend and share my interest in permafrost. And hopefully you have a new perspective on looking at the landscape when you go drive along a bumpy road with frost heaves and troughs from degrading ice wedges, or just when you fly into Fairbanks, look down at the Tanana Flats and look at those drowning forests.
Tor, I'll just jump in here. Thanks very much for your presentation. It was wonderful. Really good to learn the complexity of it. Just a quick reminder for folks, we're going to hear on May 11th from Rick Steiner talking about the effects of climate on marine ecosystems. And then we have one on June 8th with Zav Grabinski talking about climate and fire in Alaska. So thank you for joining us this evening. Really appreciate it. Oh, and we'll make this recording available for folks on the Alice's website.
Thank you,
Well, I see a lot of
everybody.
friends on there. Yeah, good. Thanks for attending, and great to see you all.
Thank you very much, Tor. This was wonderful.
Okay.
Thanks,
Bye now.
Tor.
Looks informative.